I have that it's 3 o'clock. Aditya, are you ready to go?
Yes. So thank you for the opportunity. So
Okay.
I'll be speaking.
Let me introduce you. So our last speaker for today will be Aditya Tiwari, speaking on the eigenvalues of the Laplacian on ellipsoids with curvature conditions.
Okay, so I'll be speaking about the eigenvalues of the Laplacian on ellipsoids with curvature condition. So first I will talk about some preliminaries, and then I will talk about the motivation behind the problem, and then we'll see the statement of the main theorem, and then we'll see a rough sketch of the proof. Okay, so we'll assume that Mg is a compact Riemannian n manifold of dimension n, and del G is the Laplace operator. So del G acts on the space of smooth functions on M. Okay, so if we have a smooth function f, then del G f will be trace of Hessian of f. So it is well known that the spectrum of this negative, so minus del G. So this is a non-decreasing sequence. So if we have, so the first eigenvalue is 0, and all the other eigenvalues are positive, and we can arrange them in an increasing sequence. And each eigenvalue will occur in this sequence as many times as its multiplicity. Okay, so we'll look at an example. So if we look at the spectrum of the Laplacian on unit sphere, so the first eigenvalue will be n. So for any dimension, so if we take Sn, so first eigenvalue will be n. So we'll define the notation. So the ith eigenvalue of the Laplace operator, we'll call it to be delta I G naught. Okay, so here G naught is the standard Euclidean metric on Sn. So with this notation, we have that lambda 1 G naught is n. Okay, so in case of two spheres, so we have that these eigenvalues are L plus 1 with multiplicity 2L plus 1. So we'll see in a few minutes that why we have discuss this example. So there is a very famous theorem of Lichnerowicz. So it states that so for compact n Riemannian manifolds, so if there exists a positive number k such that this Ricci curvature is bounded below by k, then the first eigenvalue of this compact Riemannian n manifold, so it will be greater than or equal to k by n minus 1 times n. Okay, so for compact Riemannian n manifolds, with the property that this Ricci curvature is bounded below by n minus 1, then this Lichnerowicz theorem says that this first eigenvalue will be greater than or equal to n, because here we are taking k to be n minus 1. So Lichnerowicz theorem compares the first eigenvalue of any compact Riemannian n manifold with that of the first eigenvalue of the unit sphere. Okay, so a very natural question which arises from here is that do we have that lambda ig greater than or equal to lambda I G naught for all I greater than or equal to 1, where this if we take any compact Riemannian n manifold. So this is the question, that do we have this? Now the answer to this question in general is no. So it was shown by Donnelly. So he constructed a counter example in dimension 4. So this counter example, so it can be extended to higher dimensions also. But in dimension 2 and 3, so this problem is still open. So Mangasuli, so he showed that this inequality holds in the following two cases. So in dimension 2 and 3. So if we have that so this is for dimension 3. So if we have that Ricci curvature of a left invariant metric G, so on S3, so it is greater than or equal to the standard metric on G naught, then this eigenvalue inequality holds for all I greater than or equal to 1. Similarly, so if we have so this is for dimension 2. So if we take S2 G, where G is a metric which we obtain by perturbing G naught through rotationally symmetric and conformal matrix, then also we have that this eigenvalue inequality holds. Okay, so we have shown that this eigenvalue inequality, so it holds for ellipsoids also with curvature condition. That okay. So with these two examples, so we believe that this eigenvalue inequality, so it holds for all eigenvalues. So we still believe we are not sure. Okay, so first we'll define that. So here this this Ricci curvature condition. So in case of dimension 2, so this Ricci curvature is k times g. So where k is the Gaussian curvature. So this bound on the Ricci curvature, it can be converted to bound on the Gaussian curvature in case of two manifold. Okay, so this question can be rephrased as, so if we have a compact Riemannian two manifold with Gaussian curvature bounded below by 1, then do we have that this eigenvalue inequality holds for all I greater than equal to 1. So we have shown that if we take an ellipsoid which we obtained through perturbation of unit sphere, this Gaussian curvature is bounded below by 1, then given any L in N, so there exists an epsilon naught. So it depends on the this curvature condition. Okay, so there exists an epsilon naught such that for all 0, so for all epsilon between 0 and epsilon naught and all the eigenvalues, so between 0 and LL plus 1, we have that this lambda I g epsilon is greater than equal to lambda I g naught. Okay, so here g naught is the standard Euclidean metric and g epsilon is the metric induced on this ellipsoid. Okay, so here we have seen that we are using ellipsoids and then perturbation. So we'll define the notations. Okay, so we'll denote EABC to be this ellipsoid, x square by a square, y square by square, plus z square by c square equal to 1. Okay, then based on the semi-axis lengths ABC, so we have that we can classify ellipsoids in two types: biaxial ellipsoids and triaxial ellipsoids. So we have two different type of biaxial ellipsoids, EAAB and EABB. So here EAAB, so we have that bigger axis lengths are equal, and EABB, so here the smaller axis lengths are equal. Okay, so now we'll look at the perturbation which we are taking. So we'll assume that A is 1 plus alpha epsilon, and B is 1 plus beta epsilon, and C is 1 plus gamma epsilon. Here alpha, beta, and gamma are fixed, and epsilon is positive. Okay, then this family of ellipsoid, so this is the family. So we represent it by EABC epsilon. So if we take epsilon equal to 0, so this is a unit sphere. And for epsilon near 0, so this is close to this unit sphere. So it is a perturbation of the unit sphere. Okay, so we'll call the metric obtained by restriction from R3 to be G epsilon. Okay, then now we'll obtain the condition on the same axis length for the curvature. Okay, so we have that if you take a point P on the ellipsoid, then this Gaussian curvature Kp, so it is given by this formula. Okay, so if we want that this Gaussian curvature is always greater than equal to 1 for all points on this ellipsoid, so this is true if and only if this minima of this curvature, so it is greater than equal to 1. So we'll compute the minima. So this minima is computed using Lagrange's multiplier. So this minima of Kp, so it exists on the following 6 points. So these points are the points where the ellipsoid cuts the axis. Okay, so these are the extrema points with the following extremum values. Okay, so if we assume that A is greater than B, greater than C, greater than 0, then we have that K min is C square by A square B square. Okay, so we have found out the minima. Now we'll find out the condition on semi-axis lengths for this K min to be greater than equal to 1. So first we'll look at the biaxial ellipsoids of the type EABB. So here minima will be 1 by A square. So this will be greater than equal to 1 if and only if we have that 1 is greater than equal to A, greater than B, greater than 0. Okay, so if we use this condition, then we obtain the following condition on the perturbed ellipsoid. Okay, so K min will be greater than equal to 1 if we have that alpha is 0 and beta is less than 0, and epsilon is between 0 and -1 by beta. Okay, so here we have two different type of ellipsoids. So, but in this case, so we have that epsilon lies between alpha by beta and -1 by beta. So here we can see that this ellipsoid is away from 0. So this will not be a perturbation of the unit sphere. So we'll discard this case. So now we have biaxial ellipsoids of the type EABB. So in this case, so minima is b square by a power 4. So this will be greater than or equal to 1 if and only if we have that 1 is greater than or equal to a, greater than b, greater than or equal to a square, greater than 0. So again, using this condition, we'll find out condition on this perturbed ellipsoids. Okay, so we have that k mean epsilon is greater than or equal to 1. If and only if we have that alpha is less than 0 and beta lies between 2 alpha and alpha, and epsilon is between 0 and beta minus 2 alpha by alpha square. So here we are obtaining only one ellipsoid. So this is a perturbation of the unit sphere because here epsilon lies between this near 0. Now we'll look at the triaxial ellipsoids. So in case of triaxial, so minima is c square by a square b square. So we obtain this condition that 1 is greater than a, greater than b, greater than c, greater than or equal to ab for this minima to be greater than or equal to 1. Now using this condition, we'll obtain the condition on this perturbed ellipsoid. So we have this following condition on the alpha, beta, and gamma, and so this is also a perturbation of the unit sphere because here epsilon is near to 0. Now we have obtained condition on the ellipsoids for the Gaussian curvature to be greater than or equal to 1. Now so this theorem, so there is this theorem. So they have found out the approximate spectrum of the biaxial ellipsoids. So approximate spectrum of the biaxial ellipsoid. So without any curvature condition. So here they are not using any curvature condition. So in this case, so if we have biaxial ellipsoid EAB epsilon, and here also there isn't any ordering in A and B. So the same holds for EABB also. Okay. So the eigenvalue is given by lambda g epsilon. So it is L plus 1 plus little lambda 1 epsilon plus higher terms of epsilon. So here this is the spectrum of the two sphere L plus 1. Okay, so here this lambda 1, so it is given by this formula. So it depends on alpha and beta, okay, and L. Okay, so using this theorem, so if we can show that this lambda 1, little lambda 1, so it is a positive, then we have that this is an increasing function. Okay, so we have shown that if we put the curvature condition on these perturbed ellipsoids, that this Gaussian curvature is bounded below by 1, and if we arrange these eigenvalues in an increasing order, then we have that given any L in N, there exists an epsilon naught depending on alpha, beta, and L greater than 0, such that for all epsilons between 0 and epsilon naught, we have, if we take any eigenvalue between 0 and L plus 1, so if we take any ith eigenvalue of this ellipsoid, then we have that this ith eigenvalue of the ellipsoid, so it will be greater than or equal to the ith eigenvalue of the unit sphere. Okay. Now we'll go to the triaxial case. No, so we'll look at a corollary. So this corollary says that given any L in N, so there exists a biaxial ellipsoid epsilon with Gaussian curvature bounded below by 1, such that if we take the ith eigenvalue between, so if we take any eigenvalue between 0 and L plus 1, then it will be greater than or equal to the corresponding eigenvalue in of the unit sphere. Okay, so this is for the biaxial case. Now we'll look at the triaxial case. So in case of triaxial, so this theorem is for the approximate spectrum of the triaxial case. So if we have a triaxial ellipsoid with, then its eigenvalue, so is given by this formula that we can approximate it by this. So it is L plus 1 plus lambda 1 epsilon plus higher terms of epsilon. Okay, so here this is the L plus 1 is the eigenvalue of the 2 sphere. Now here this lambda 1, so this is one of the 2L plus 1 eigenvalues of these. So we have 4 symmetric tridiagonal matrices, and they will have 2L plus 1 eigenvalues. So this lambda 1 is one of them. Okay, so we'll have for each L, so we'll have 2L plus 1 lambda 1s. Okay, now if we can show that these matrices under curvature condition, so they are positive definite, then we have shown that this is an increasing function. Okay, so we'll look at these matrices, and so their entries will depend on alpha, beta, and gamma. Okay, so these are and their orders also depend on L. So if L is odd or even, so their order will depend on that. Okay, so these matrices are tridiagonal and symmetric, and all these entries are real, and the diagonal entries are positive. Okay, so I will skip these. Okay, so this is M cos E, so this is M sin E, and these are the entries. Okay, so they depend on alpha, beta, and gamma. So this is M cos O, M sin O. So, and these are the entries. Okay, now we'll use to prove our theorem. So if we can show that these matrices are positive definite, then we are done. So we will, to show positive definiteness, we'll use this theorem. So if we have that AN is a real symmetric tridiagonal matrix, so with positive diagonal entries, and if this inequality holds, then we have that AN is positive definite. Okay, so using this theorem, so we have proved that if we suppose that alpha is less than 0 and greater than beta, greater than gamma, greater than equal to alpha plus beta, then all these 4 matrices are positive definite. So remember that these are the conditions for the Gaussian curvature of the triaxial ellipsoid to be greater than equal to 1. So we have proved. So this will imply that we have that if we take a family of triaxial ellipsoids with curvature condition, that this Gaussian curvature is bounded below by 1, and if we arrange these eigenvalues in an increasing sequence, then we have that given any L in M, there exists an epsilon naught depending on alpha, beta, gamma, and L, such that for all epsilons between 0 and epsilon naught, we have that the ith eigenvalue, which lies between 0 and LL plus 1. So it will be greater than equal to the ith eigenvalue of the corresponding unit n sphere, the unit 2 sphere. Okay, so this leads to this corollary that given any L in N, so there exists a triaxial ellipsoid epsilon with Gaussian curvature bounded below by 1, such that if we have that this ith eigenvalue is between 0 and LL plus 1, then it will be greater than the corresponding ith eigenvalue of the unit 2 sphere with this standard Euclidean metric. Okay, so these are the references. So this is the paper from where we have used the theorem for the approximate spectrum, and these two are for for the reference from the literature survey. So they, and this is from where we have used the theorem of positive definiteness. Okay, thank you.
All right, let's all thank Aditya. Does anybody have any questions? No questions? All right, well, if not, let's thank Aditya again.